Hello everyone, my name is Usman Aslam and I'm a reservoir engineer with Exploration and Production Software, which is a division of Emerson, and I'm excited to be here to talk about assisted history matching using Tempest ENABLE. During this presentation, I will talk about what the history matching in general is and why do we need it, two different approaches typically used for history matching, different Tempest ENABLE workflows, and how Tempest ENABLE can be used for assisted history matching, what is the end product of assisted history matching, and how can we use it for probabilistic forecasting and scenario testing. And at the end, I will conclude my talk. So what the heck is history matching? Well, it's the process of adjusting a subsurface model until it closely reproduces the real reservoir behavior. This process is sometimes also referred to as model calibration or data assimilation. So to explain this concept, I'm comparing observed response from my reservoir against the response which my reservoir simulator has produced. And as you can see on this plot, that the response from the numerical simulation model is not only under-predicting the water production by almost 15%, but also has 1 year delay in the start of water production compared to the historical observation from the field. So what we need to do is to actually calibrate or adjust various aspects of this model until it matches with the real observations or measurement from the reservoir, and that is what is known as history matching or calibration process. So the next question really is, what are we trying to achieve by history matching? The main reason we need to calibrate this subsurface model is because we want to use it to reliably predict the future performance of the reservoir with a high degree of confidence. And apart from that, we would also like to understand the uncertainties in different modeling domains and as well their impact on future production forecasts. So if you look at the two pictures on the left hand side, you will see that we only truly know about the reservoir properties where we have drilled the wells, and we use different geostatistical algorithms to populate properties in between and beyond wells. So we may have high degree of uncertainties in these properties. And if you look at the picture on the right hand side, you will see likewise we may have two different set of relative permittivity curves resulted from two different interpretations of the special core analysis. So we want to understand these uncertainties and their impact on the future production from the reservoir as well. And that is precisely why we need to calibrate our model to historical data. So there are two approaches used to perform history match. If you do it yourself, it's called manual history match, and if you use some computer-based program to get assistance, then it's called assisted history match approach. So now I'm going to compare manual versus assisted history match. So in the manual history match approach, you can only change one or maybe two parameters at a time, but the assisted history matching approach allows you to change large number of parameters to measure their impact on the production. And in the manual history match approach, the parameter selection is purely based on the knowledge and the experience of the reservoir engineer. While in the history match approach, assisted history match approach, the parameter selection is based on the statistical algorithms. Manual history match process is a sequential matching process whereby you would match your pressure first and then your saturation dependent properties like gas oil ratio and water cut. On the contrary, the assisted history match is a simultaneous matching process where you would match everything in one go. Since you are only running one iteration or one variant of the model in manual history match approach, so you cannot really take advantage of all the computational resources we have available today. But on the other side, since you can submit multiple variants of the model at the same time, so you can really take advantage of the available computational resources. Manual history match would typically result in one best history match model because that's what you're really trying to do. You are only running one variant of the model at a time, while on the other side, assisted history matching helps you identify multiple history match models. And then since you only have one history match model in manual history match approach, your production forecast would be very deterministic, while this history match would allow you to have probabilistic production forecast. So where can you use Tempest Enable? Well, Tempest Enable can be used at any stage of the field life, starting from bid appraisal to the abandonment of the field. And here I have listed some of the workflows where you can use Tempest Enable, and I'm going to describe these workflows a little bit more in detail in the next couple of slides. So you can use Tempest Enable for sensitivity analysis, where it would allow you to identify the most influential parameter, the parameter that has the most impact on your production, and then it also helps you reduce the number of parameters for efficient history matching. So once you have identified the most influential parameter and you have a reasonable of parameters you would like to change, then you can move on to this history match, where Tempest Enable will allow you to improve the predictability of the model by helping you identify multiple calibrating models. So if you're using Tempest Enable, then you can capture the uncertainties in your simulation model as well as in your static model. And I'll come back to that. This process is called big loop. I'll show you how it looks like later on. And then the end product from assisted history match is not one single model. You will get a collection of best history match model which is characterized by the posterior distribution, and I'll describe what the posterior distribution is later on in my slides. Alright, so once you have obtained a satisfactory history match and you have multiple history match model, then you can calculate the posterior distribution like I said, and then you can use that for probabilistic forecasting, which is what you really need for the decision support in field development planning. Tempest Enable have ensemble based prediction workflows that allows you to test different scenarios, and that helps you to avoid taking suboptimal decisions, right? And then you can use this prediction under uncertainty workflow for both the green fields where you don't have historical data and the brown fields where you would have historical data. So once you have identified the optimal feature development plan, then you can further optimize, you can use the optimization workflow in Tempest Enable to optimize various user control parameter to optimize an objective function, which is usually an economic one. For instance, you might want to optimize the net present value, or you might want to reduce the upfront cost of a certain field development plan. The ultimate purpose is to increase the profitability from your field by maximizing the reservoir performance and reducing the operational cost in the future. So the assisted history matching workflow in Enable is very similar to the manual approach, and that is not really surprising. It's a good workflow, it's easy to understand, so why do we want to change it? Enable is meant to make the life easier for the engineer, and having a familiar workflow is part of that. So the difference is in who does what. The three activities you see in the blue or the light blue box are done by Enable instead of the engineer. So Enable will select the parameter values for each run. Enable will run the simulation and then compare the simulation results against the historical data before the loop repeat itself. So if you're using Tempest Enable, you would not have to limit yourself to just the dynamic model. You can also hook up the static model as well in the loop. So what you would need to do is to actually specify what parameter you would like to change in your static and in your dynamic model, and the rest of the workflow would be same as the previous workflow. The only difference would be that Tempest Enable will generate the geological model from your geomodeling package, and then it would upscale it to the reservoir model, and then you would run the simulation, compare the results, and then the loop would repeat itself, and that would ensure that the simulation model is consistent with the geological model. Okay, so this is this provides an overview of assisted history matching using Tempest Enable. So you begin with preparing your simulation model, which you then import into Tempest Enable. You define the modifiers and their attributes, set of initial set of scoping runs, and then you import the observed data, validate your model. If the model is valid, then you move on to the next step. Otherwise you would go back and change the maybe ranges, or even introduce new modifiers, or might want to even reconsider the construction of geological model. So let's say you have validated your model. The next step would be to tell Tempest Enable where you would like it to focus matching. That's done by setting up the history match point and their tolerances. So once you have done that, you would set up batches of informative runs, which use machine learning algorithms to find multiple best history match models. So once you have obtained the adequate match, then you move on to the probabilistic forecasting, which is the next workflow in the chain, in the modeling chain. If you have not obtained a satisfactory history match after a batch of informative runs, then you will go back and maybe revise your history match point and their tolerances until you have obtained a satisfactory match. So just to provide you a little bit more details of these steps. So to begin with, you would select the simulator. Tempest Enable is simulator agnostic, which means that you can use it with all the mainstream simulator in the market. So you can use it with Eclipse, Tempest More, Navigator, Nexus and VIP, and other bespoke simulator like Gigapowers from Saudi Aramco. So once you have selected the simulator, you import your simulation model in Tempest Enable, and then you can set up the modifiers, which is a technical term for uncertain parameters or uncertainty parameters. You specify the ranges, and you then choose distribution and the transform for those modifiers or the uncertain parameters. Once you have done that, you fire off scoping runs, where the purpose is to sample the solution space. So we use lateral hypercube sampling, where Tempest Enable will generate 1500 samples or 1500 LSC samples, and choose the best ones by maximizing the minimum interpoint distance. The whole purpose is to validate the initial parameterization. So once you have done that, you would import the historical data. You can import either the time dependent data or the depth dependent data, and once you have done that, you would be able to validate your model. So you would check the coverage and compare the trend. I have included an example of a invalid model and a valid model. For a valid model, the scoping run would bracket the historical data and the response is more or less similar, and vice versa for the invalid model, where the response is neither similar nor the scoping runs are bracketing your historical data. In that case, you want to go back and maybe revise your geological model and modifiers as well. So once you have validated your model, you would set up the history match point. This can be done interactively on a 2D plot. You double click, and then Tempest Enable will add an estimator point where you double click, and then you can also interactively change the ranges, and then also change the position of these estimator points. So in this case, I have set up 2 estimator points on my cumulative oil production. So that's how I tell Tempest Enable where I would like you to focus matching and what is important for me. So that's how you really bring in your engineering judgments, right? So once that is done, you will move on to setting off a batch of informative runs. That's where you get to choose from available set of state-of-the-art machine learning algorithms. Tempest Enable use these machine learning algorithms to improve the match, and then also calculate the posterior distribution, again, which is what is needed for the probabilistic forecast. So you do not only end up from the history match, you do not only end up with one good matched model, but you end up with a collection of good models which you can then use to reliably forecast the production. So let's see how the history changes the distribution. Here I have a 2D example where modifier x1 has a user specified prior distribution that is uniform, and then modifier x2 has a triangular distribution or triangular prior distribution. The sampling density is shown with each one being equiprobable. After history matching, the distribution has changed. So you see, after I did the history matching, the prior distribution has changed. And this is what will be used when calculating prediction confidence intervals. So this slide demonstrates what history matching is really for. The engineer's prior belief have been replaced by a distribution that reflect the weighting derived from the history match, and that is precisely what the history match is all about, that you calculate the posterior distribution, which is what you use for the probabilistic forecasting. You do not need, you do not want to have just one single model which you can then use for predicting the future. What is posterior distribution? Posterior distribution is a conditional probability distribution. So for example, what is the probability of something given an event has occurred, right? So the modifier values which give a good match to the data will have a higher probability than the modifier values that give a good match. And when we calculate the confidence interval for the future forecast, for the prediction, we do take into account all these runs. All right. Moving on. So once you have a stable posterior distribution, then you can create the posterior ensemble, which will be sampled from the posterior distribution. That is done at the end of the history match. Once that's done, then you can create a prediction ensemble to model a certain future development plan, and that would be based again on the posterior ensemble. So here I'm comparing my informative runs with the initial scoping runs, and as you can see, the uncertainty in these informative run has gone down a lot. So that's an ensemble of good history match cases, and then once I have these best history, a collection of best history match cases, I would have posterior distribution, which is what I would use to forecast the production. And Tempest ENABLE will also calculate the confidence interval for the future prediction. All right. So like I said at the beginning of my talk, that Tempest ENABLE has ensemble-based prediction workflow that allows you to test different scenarios so that you can avoid suboptimal decision by selecting the right field development plan. So in this slide, I'm comparing different field development plans. So that is the end of the history after 7 years. And then this prediction ensemble represent no further activity. So in this case we had been water flooding during the history period, and we just wanted to see what would happen if we just continue water flooding, do not change anything, do not introduce any well, or change any the depletion strategy. So then I can quickly use Tempest ENABLE to create a new ensemble representing a different future development plan. So this particular plan represents the infill well, where I have drilled 5 additional wells, and then I can also test different depletion strategy. For instance, in this particular ensemble, I am injecting water alternating gas using CO2, and then the last ensemble represent future prediction for CO2 injection. So it's very easy to create these ensembles and compare those against the base ensembles to see the incremental oil you get. And then you can also calculate what we call the delta ensemble, where you can subtract base ensemble for all these ensembles for direct comparison to see the incremental oil you would get from different scenarios. All right. So during the course of this presentation, we saw that the history matching is all about calibrating your reservoir model or the numerical model with the historical data. And the reason we need to do that is to be able to use that model to reliably forecast the production. And then we talked about advantages of using assisted history matching approach over manual approach. And then we talked about the different workflows you can use in Tempest ENABLE. For instance, you can use assisted history matching, sensitivity analysis, prediction or probabilistic forecasting, and the optimization workflow in Tempest ENABLE. And you do not have to limit yourself to numerical simulation model, but you can also hook up your geological model in the loop to capture the uncertainty in a static model as well. The end product we saw from Tempest ENABLE is not just a single history match model, but you get a collection of good history match models and a posterior distribution, which is what you use for probabilistic forecasting, which is reliable compared to the forecast based on single best history match case. And then we also saw that you can use ensemble based prediction workflow for scenario testing to avoid suboptimal decisions. And that is the end of my talk. So if you have any questions, you can write to me on usman.aslam@emerson.com. So that's my first name dot last name at emerson.com.